Look at the room you're sitting in. You can name everything in it. The walls, the light, the air, the weight of your own body in the chair. It all feels complete, and the completeness is the part nobody thinks to question. Nothing seems missing, nothing asks for attention, and nothing hides. Almost none of it is reaching us. The visible spectrum we see is a sliver of the radiation crossing that room right now. The matter we can touch is a small fraction of the mass holding the room and the building and the planet together. And something is stretching the space between all of it while we sit still. We built a civilization on what we could see. Then we built instruments to measure the spectrum and the matter and the energy around us, and they kept sending back the same answer. There is more. There is far more. And most of it does not respond at all. Tonight we take that room apart. Not with wonder, and not with a tour of distant objects. We look at what is already here, already crossing us, already deciding how everything we can see is going to end. I keep coming back to one question, and I cannot make it sit still. Are we looking at the world? Or only at the small part of it that agreed to talk to us? Stay in that room one more minute. Look at the space between you and the far wall. To us it reads as empty, just air and light, and nothing worth naming. Now think about what is actually crossing it right now, in the seconds you have been reading this. Voices are crossing it, on frequencies nobody in the room is tuned to. Our skin pours infrared radiation into that room, about 100 watts of it, every second we sit there. That is a bright bulb burning in the middle of the room, and nobody can see it. Is the room empty, or is it simply not talking to us? We sit inside a crowd and call the place empty. We did not always know this. In 1800, an astronomer named William Herschel was doing something very simple. He split sunlight with a prism and set a thermometer under each color of the spectrum to see which one carried the most heat. Red ran warmer than blue, which probably struck him as a small curiosity, and nothing more. So he slid it one step further, past red, into the part of the bench where the spectrum had no color at all, into the dark. The reading climbed. It went higher than under any color, higher than red, higher than all of them. Think about reading a letter through a slit in the envelope. The line is real, the words are correct, and we read them carefully. Then we describe the letter to somebody. That is the honest mistake, and we are not lying when we make it. We report exactly what reached us, but a whole page is being described from a strip of it, and nothing in that strip suggests the page is larger. Herschel had found the first line outside the slit. Infrared radiation, moving at light speed, carrying real energy with no color attached. Within a century, we had the rest of them. Radio, microwave, ultraviolet, and the short, violent wavelengths of the electromagnetic spectrum that pass through walls and through people. Every wavelength had been crossing every room we ever sat in. None ever announced itself. So what does that do to the word room? You still feel sure about that space. That certainty came from somewhere, and I would argue it never came from measurement. It came from the fact that nothing in there ever needed you. We did not build our picture of the world out of the world. We built it out of whatever happened to knock. Which leaves a question I would rather not ask. Why that particular knock, and none of the others? So the slit is narrow. How narrow? We can write that number down, and I would rather you saw it than took my word for it. James Clerk Maxwell settled the shape of it in 1865, when he showed that light and radio and heat were never separate phenomena at all. They were one family of electromagnetic waves, sorted only by the wavelength of each one. Everything from wavelengths shorter than an atom to the slow ones rolling across whole cities belongs to one spectrum. One continuous range, one family, one rule. Our eyes answer to a strip of that range about 300 nanometers wide. 300. Out of everything. Numbers that small stop meaning anything. So let us put the whole range somewhere we can walk on it. Imagine we stretch the whole electromagnetic spectrum out as a road. New York to Los Angeles, 4,000 kilometers, every wavelength laid down in order of frequency. Somewhere along that road sits the narrow band our photoreceptors respond to. It is not a stretch of road. It is not a town on the road. It is a line roughly 1/10 of a millimeter across, thinner than a single sheet of paper lying flat on the asphalt. Every sunset you have ever watched arrived through that sheet of paper, and probably everyone you will. Every face you love. Every color you tried to describe to somebody and failed. All of it arrived through a gap you never chose and cannot widen. And here is the part I cannot get past. We did not walk the road and then choose the paper. We were handed the paper and told it was the road. Nothing about standing on that road tells us anything lies to the left or the right of us. From where we stand, the road does not look like a road. It looks like everything there is. So we should look again at what the word visible is doing in a sentence. Visible is not a property of the world. We seem to be reading a report on our own equipment and treating it as a report on the world. Do you see the swap? It happened so early that no language on this planet appears to mark it. We call the rest of that spectrum invisible, which sounds like a statement about radiation. It is a statement about a receptor in our heads. So if we are working from a band that thin, something upstream decided where to cut it. What was doing the choosing, and what did it want? Something did the cutting, and it was not one thing. 3 filters, stacked one behind another, and none of them cared what we would eventually be able to know. Start with the star, because I think that is where it begins. Our sun does not radiate evenly across the electromagnetic spectrum. Its output peaks in a fairly narrow band, and the peak sits almost exactly where our eyes are most sensitive, near 500 nanometers. That is not a coincidence, and it is likely not a design either. It is probably the cheapest place to build a receptor, because that is where the energy already was. Free light, free signal. No work at all. Next comes the atmosphere. Most of the spectrum never reaches the ground at all. The air overhead absorbs ultraviolet radiation, absorbs most infrared wavelengths, and blocks the short violent frequencies entirely. It appears to leave exactly 2 windows open. One of them is radio, the other is the strip we see with. Then comes water. Every eye ever built was made of wet tissue. Water is stubbornly transparent in one narrow region of the spectrum, and stubbornly opaque almost everywhere else. The first photoreceptors formed in the ocean, and the ocean had already decided what reached them. 3 filters, and I want to be clear that none was ever consulted. All of them upstream of you, and of everyone who ever opened their eyes and felt certain about the world. Now think about a dog whistle. You blow it, you hear nothing, and the dog across the room turns around. Nobody watching that concludes the whistle is silent. We know the sound is there because the dog told us, and we accept without argument that our ears are narrower than the room. Why is that so easy to accept about your ears? So why is that impossible to accept about your eyes? That is where the comparison stops being comfortable. With sound, something in the room answered for us. With light, for almost the whole of human history, nothing in the room ever did. No animal turned around. No creature we lived alongside reacted to the infrared radiation pouring off our bodies. The room looked empty, and every living thing in it agreed. We were not deceived. We were tuned to a star, filtered through an atmosphere, and assembled out of seawater. And if the equipment was built by pressures that never once aimed at accuracy, what exactly are we trusting when we trust it? So one filter sits in front of the eye. That alone is uncomfortable. Nobody warns us about the second filter. We carry it behind the eye, inside the equipment we are using right now. We talk about vision as if the eye were a window. Light comes in, an image goes back, and somewhere in the head we sit and watch it. That is not what the hardware does. I find the real version harder to live with. The retina holds roughly 126 million photoreceptors, every receptor firing at once, all detecting radiation in parallel. The optic nerve carrying that output to the brain has about 1 million fibers. So how much of that signal can physically fit through? So we did the division, and the answer was worse than expected. 99% of the signal the retina detects never leaves the eye and never reaches the place where we experience seeing. We measured it. It is real. It goes nowhere. Think about a company where 400 people spend every day writing reports on what they measured. At 6 o'clock, one of them walks out with a single page. That page is the only thing anybody outside will read. We meet that person every evening. We believe we have met the company. That page is not false. We assembled it honestly, out of material that existed, by people doing their jobs. But no line on it tells us how much stayed on the desks. The retina does not transmit a picture. It transmits edges, movement, and changes in the density of incoming radiation. The brain assembles the rest of that image out of expectation, spending as little energy as it can on actual measurement. So most of what we are seeing right now was probably never measured at all. It was predicted and then confirmed cheaply, because prediction costs less energy than measurement. And that is where the machine stops being a measuring device and becomes a survival device, built by pressures that had nothing to do with truth. I think the priority was never accuracy. We were built for speed, and a fast wrong answer beats a slow correct one when something large is moving toward us. Your eyes did not evolve to show you the truth. They evolved to keep you alive long enough to reproduce. Those are not the same job. So how would we ever catch it working? What does a gap in your own vision look like from the inside, when the thing reporting the gap is the same equipment that made it? We can catch it working, and I want you to catch it yourself. We have been able to since 1660. There is a hole in the back of each of your eyes. You have never once seen it, and neither has anybody else. Where the optic nerve leaves the retina, there are no photoreceptors at all. No receptor cells, nothing to catch the incoming radiation and turn it into a neural signal. It is a blind patch a couple of millimeters across. Radiation landing on that patch produces no signal whatsoever. At any wavelength, at any energy. You carry 2 of these blind zones on your retinas, 1 per eye, your whole life. Edmond Marriott worked this out and then did something clever with it. He showed the French court that we could position a man so that another man in the room simply lost his head from view. Not blurred, gone. And the wall behind him carried on as though nothing had ever stood there. We were watching a neural repair happen and could not see it. Try it later with a dot and a cross on paper, because reading about this is weaker than doing it. Close one eye, move the page slowly, and at some distance one of the 2 marks on that paper will simply vanish. Not fade, vanish. No signal at all. Here is the part I keep coming back to. When the mark disappears, we do not see a hole. We do not see darkness or noise or a missing patch. We see wall. Solid, continuous, complete. Think about wallpaper with a small tear in it. We patch it with a piece cut from the same roll, matched and pressed flat. Stand back and our wall looks whole. Now imagine the patching happens by itself, instantly, every time we look, with no seam and no way to locate the repair. We would never learn the tear was there. The wall would simply be a wall, and we would go on describing it as one. That is what your brain does with the blind spot, continuously, for an entire life. The blind spot never reports itself. It fills the gap with whatever pattern is nearby, and hands us the finished image. So we have an optical system that discards most of its input. It predicts a large share of the output, and covers its own holes without mentioning it. And we have been using that system to decide what exists. Does that sound like an instrument to you? If our own optical equipment can close over something the size of a face, what else has it been quietly covering? And what would it take for any of us to notice? So our instrument closes over its own gaps. The obvious move is to stop trusting the instrument and start trusting the arithmetic instead. In 1930, we tried exactly that, and the arithmetic sent us somewhere nobody wanted to go. I still think it is the strangest turn in the whole story. We were studying beta decay. A nucleus of one element quietly turns into another and throws out an electron, and you can measure both ends of that with real precision. Energy in, energy out, and the 2 columns of the ledger are supposed to match exactly. That is not a preference of ours. Conservation of energy is the most heavily tested rule we have. The columns refuse to match, no matter how carefully anyone measured the decay or how much we improved the equipment. Energy kept going missing. Different amounts each time. Momentum went with it. Think about a household where the money never balances. Your household, if it helps. Every month a portion is gone, never the same portion twice, and no receipt accounts for it. Anybody sane starts by doubting their own arithmetic, because arithmetic is the cheapest thing to blame. But suppose we check the sums 1,000 times, and they come out perfect. Then, we are left with the other explanation, and it is far worse for us. Somebody is carrying money out of your house through a door you have never found. Wolfgang Pauli took that second option, and I doubt he enjoyed it. In December 1930, he wrote to a meeting of physicists at Tübingen and proposed a particle nobody had ever seen. No charge, almost no mass, and it was quietly carrying the missing energy and momentum straight out of the room. He called it a desperate remedy, and he meant it. By his own account, he felt he had done something a physicist should never do. He had invented a thing that could not be detected by any means then available, and he said so in writing. Enrico Fermi gave it a name 4 years later. Neutrino, the little neutral one. A particle defined entirely by what it refuses to do. So our arithmetic had told us something our equipment could not confirm. There was more in that room than we could reach, and the only sign of it was a shortfall in a ledger. How long do we keep believing in something on the strength of an absence? How long would you? And what would it actually take to catch one? It took us 26 years, and the answer arrived from a place nobody would have guessed. Frederick Rains and Clyde Cowan understood that our problem was never sensitivity. It was numbers. A neutrino almost never interacts with matter. The only way to catch one is to stand in front of an absurd flux of them and wait. In 1956, they parked their detector beside a nuclear reactor at Savannah River, because a reactor core pours out antineutrinos by the trillion every second. That was the whole idea. Go where the flux is. So we filled large tanks with water and a chemical that flashes whenever the right nuclear reaction occurs inside them. Then they watched for one specific double flash, the signature of an antineutrino striking a proton. They found it, and I still think the telegram is one of the great sentences in physics. They wired Pauli to tell him the particle he had apologized for was real. 26 years of absence, closed by 2 flashes of light in a tank of water. Now, hold the next number for a second, because it applies to every one of us. Roughly 100 trillion neutrinos pass through the mass of your body every second of your life. Not once in a lifetime, every second of it. They arrive from the sun, from the nuclear cores of distant stars, from radioactive decay in the ground under our feet, through the skull, through the chest, through the chair, through the floor and the planet and out the other side. Think about standing outside in heavy rain and staying completely dry. Not sheltered, not covered. The water passes through us as though we were open windows, and we would never learn it had rained. Do you feel anything crossing you right now? We usually take being untouched as a sign that nothing was there. And here I think those two ideas come apart permanently. Is being untouched the same as being alone? Something can cross us 100 trillion times a second and leave no mark at all. We would probably never have looked for them. There was no gap in our senses to notice, because a gap implies that something failed to arrive. Nothing failed. Our arithmetic went looking on our behalf, and it found a river running through the house. 100 trillion of them passed through your heart while you read that sentence. Not one of them noticed you were there. So what else is arriving right now that leaves no mark on any of us? The obvious repair is to build better equipment, and we did exactly that. Herschel found infrared in 1800. Ultraviolet followed a year later. Radio arrived in 1888. The short, penetrating wavelengths in 1895, and the hardest radiation of all around 1900. 5 new bands of the electromagnetic spectrum opened in a single century, and every one of those wavelengths had been arriving the whole time. Nobody missed them. Nobody could have. No signal had ever failed to show up. So we widened the slit, band by band, decade by decade. That is real progress, and I do not want to talk you out of it. But look at what a detector actually is, before any of us relaxes. Do you know what you are holding when you hold an instrument in your hand? Here is what I keep running into. Every instrument ever built was designed to catch something we already had a reason to expect. Pauli imagined the particle first, and only then could we build a tank and watch for the flash. The order matters more than it sounds. An idea has to arrive before the hardware does, without a single exception in the history of measurement. A detector is a question with a plug on it, and a question can only be asked about something already thought of. Think about a net with a fixed mesh. We drop it, haul it up, and study what came out of the water. The catch is real, and every measurement we take of it is honest. Then we write down what lives in that sea, and none of us is lying. Your net, your data, your conclusion about the mass of life in that water. Notice what quietly happened. We described an ocean using an object built to let most of that ocean through. Nothing in that net can tell us the size of what escaped. Nothing ever will. The net has no opinion about water. So what are we really saying when we call something undetected? That is our position with every detector on this planet. They are all nets. They extend the slit and never remove it. We cut the mesh ourselves, using expectations built by the same filtered sensors we were trying to escape. So is the honest question really what have we seen? The one that matters, and I'm not sure it is answerable, is what we never had reason to look for. And there is one place where that question stopped being philosophical. The arithmetic broke again in public, and this time it had nothing to do with light or radiation at all. It was about weight. In 1933, a Swiss astronomer named Fritz Zwicky pointed a telescope at the Coma cluster. It is a swarm of roughly 1,000 galaxies bound together by gravity, and what we did there was very ordinary. He measured how fast they were moving, and I want you to notice how ordinary my description of it sounds. There is a standard way for us to turn that into a mass. We watch how quickly members of a cluster orbit each other, and we apply the physics. The velocity tells us how much matter is holding them in. Faster orbits mean more mass. We use the same logic for a satellite over our heads, and we trust it enough to fly people on it. Then, we come to the second measurement. Zwicky counted the light. He added up every galaxy he could see, and worked out how much visible matter was present in the swarm. That gives us a second mass, and we can lay it beside the first. The two numbers we had just produced did not match each other by anything close to a reasonable margin. Not a correction, not a rounding error, not a bad night. The cluster moved as though it held some 400 times more mass than anything visible in it. Think about lifting a cardboard box somebody left in your hallway. It looks empty, so you brace for nothing, and your back tells you instantly that it is loaded with something. In that moment, none of us doubts the weight. We doubt the box. We assume something is inside that we cannot see through the cardboard. Nobody is ever tempted to conclude that weight has stopped working. Zwicky did the same thing, and he did it with a whole cluster. At the velocities he measured, those galaxies should have scattered long ago. Nothing visible was holding them in orbit. Do you see the shape of the problem? So he proposed that most of the mass in that cluster is simply dark, and he used the German phrase for it. Dunkle Materie, dark matter. Whole decades before anybody was ready to take the idea seriously, and long before it could be tested. Then almost nothing happened for 40 years. We left his measurements sitting there, published and largely ignored. One strange cluster is easy for us to file away as a bad reading from a difficult man. So what would it take for us to stop calling this one strange cluster? What would make the problem impossible to leave alone? What made it impossible to leave alone was a woman working on a question nobody considered important. In the 1970s, Vera Rubin and Kent Ford began measuring how fast stars orbit inside galaxies. We started with Andromeda, our nearest large galaxy, and I doubt anyone expected trouble from it. I certainly would not have. We already knew what the answer had to look like, Because your own solar system tells you. Mercury tears around the sun at about 47 kilometers per second. Neptune, far out at the edge, crawls along at 5. Do you see the pattern we were expecting? Mass sits in the middle, gravity weakens with distance, and orbital velocity drops off as we move outward. That is not a guess of ours. It is the arithmetic that lands our probes on other planets, and it has never let us down. Then, we measured the orbital velocity of the outer stars, far from the bright center where all the visible mass sits. They were not slowing down, not a little, not at all. They were moving as fast as the stars near the middle. Think about coins laid out on a turntable. Spin it slowly and every coin holds its place. Spin it faster and the outer coins go first, every time, because less is holding them the further out they sit. That is probably obvious to you. Now imagine you spin that table hard and nothing moves. The coins of the rim stay exactly where they are. None of us would conclude we had discovered new physics. We would put a hand under that table and start feeling around for the glue. Rubin reached under the table and found nothing there. So she checked another galaxy, and then dozens more. We got the same flat rotation curve back every single time, in ordinary spiral galaxies, in quiet corners of the sky where nothing dramatic was happening. That is what finished off the easy answer for us. One strange cluster is a bad reading from a difficult man. 60 galaxies is a property of the universe we live in, measured over and over. Whatever holds those galaxies together appears to sit in a vast halo of unseen mass around each one, reaching far past the visible edge. Our own galaxy is inside such a halo right now, and so are you. So how do we weigh something that gives off no light at all, at no wavelength, in no part of the spectrum? What is left to measure it with? We weigh it with light that never belonged to it, and I think this is the most elegant move we have ever made. It also handed us the worst answer we have. Einstein worked out in 1915 that mass bends the path of light passing near it. Eddington confirmed it during an eclipse in 1919. That handed us a tool nobody had asked for. Point a telescope at a distant galaxy. If something massive sits in between, the image arrives distorted and stretched into arcs we can measure precisely. Measure that distortion, and we can map the mass directly, without ever seeing what carries it. Not the matter, but the mass. The map does not care whether anything in there is shining. So we made those maps, and every one of them came back heavier than the light inside it by a wide margin. How much heavier? Enough that visible matter stopped being a useful guide to the mass of anything. Then, in 2006, something arrived that probably closed the argument. 2 clusters, 1 collision, a result nobody could talk around. 2 galaxy clusters had collided out there, and we caught the aftermath. In a collision like that, the hot gas carries most of the ordinary matter, and it behaves exactly the way our physics says it should behave. It slows. It piles up. It stays. Our lensing maps showed that the mass in those clusters had not stopped at all. It sailed straight through and out the far side, leaving every scrap of visible matter stranded behind it. I still find that image hard to hold. Look at what that leaves us holding. Think about 2 crowds running at each other down a corridor. People carrying boxes collide, drop things, and jam up in the middle. Anyone carrying nothing at all passes clean through the other crowd without breaking stride. Watching from above, we would see the pile in the center and assume that is where everybody is. We would be counting boxes and calling it a head count. The crowd went past us and never touched a thing. That is your position right now. Most of the mass around you is not slow, not hidden behind anything, and not waiting to be uncovered. It is here, and it declines to interact with your matter at all. There is something in this room with you right now. It has always been here. It simply does not have any reason to touch you. So if it will not touch anything, what would it even mean for us to catch it? What would we build? Before we build anything to catch this mass, look at how much of the universe is in question. The number changes the conversation. I do not think most of us have absorbed it. The Planck satellite spent years measuring the faint background radiation, left over from the early universe. It mapped tiny differences in the energy of that radiation across the whole sky. How it ripples depends on what the young universe was made of. So the mixture of matter and energy can be read straight off the sky. And in 2013, the accounting arrived. Ordinary matter, meaning every atom that has ever taken part in anything, comes to about 5% of what exists. 5 out of 100. That is all of it. Every star and every planet, all the gas and dust between them, the machine we are reading this on, every cell in a human body. Dark matter probably takes roughly 27% of the total. The remaining 68% is something else again, and we will come to it later in this. Brace for that one. Think about being handed your family album and told it is the complete record. 200 pages. Every birthday you had, every face you grew up with, everybody who ever mattered in that house. We know that family, and any of us would say so without hesitating. Then, somebody explains that our album holds 5 pages out of every 100 that were taken. The other 95 were never printed at all. So the album did not simply lose some photographs. It lost the ratio. It lost the scale. It lost any way for us to check it against anything. That is our position with matter, and I want to be blunt about it. Does the word everything still mean what it did a minute ago? Every phenomenon physics studied for 3 centuries, all of chemistry, every particle biology is assembled from, sits inside that 5% of the mass. We measured the leftovers. Then, we called them the universe, and we built your whole intuition about what is real on top of them. So we are not looking at a gap in the picture. We are the gap. The picture is elsewhere. And it always was. Everything you have ever seen, touched, or loved is a rounding error in the mass of the universe. So what were we actually hunting for down there? What did we expect to find? And how would we know it if we caught it? We were not hunting blindly, and this part matters more than it sounds. A search only counts as a real one if it can fail. By the 1980s, we had a candidate specific enough to be wrong, which is the highest compliment you can pay an idea in physics. Our reasoning ran like this. Whatever this material is, it carries mass and it clumps under gravity. So it behaves like particles rather than a field. It gives off no radiation at any wavelength or frequency, so we know it carries no electric charge. It passes straight through ordinary matter, so we know it ignores the strong nuclear force that binds a nucleus together. That leaves us gravity and the weak force. The weak force is the useful part because a particle that feels it will occasionally strike a nucleus and knock it sideways. Run those constraints through our standard model of particle physics, and something remarkable falls out of the arithmetic. A particle in one mass range, likely produced in the right quantity early on, lands almost exactly on the density of dark matter we measure today. The numbers converge without anybody forcing them. Nobody arranged that. It simply appeared in the equations, unasked for. Think about describing somebody to a tailor precisely enough to have a suit made for them. Height, reach, shoulders, the way they stand when they're tired. The tailor builds it, we hang it in the shop, and we wait. If the right person walks in, the fit confirms every measurement you gave. But if nobody fills that suit, year after year, the suit is not useless to you. It is telling you the description was wrong. It is the only object in that shop capable of telling you so. So we had a suit hanging in our window, and I want you to see how much a thing like that commits us. A promise with a number attached. It told us the particle should strike a nucleus in a tank of liquid a handful of times a year per kilogram. One tiny flash of light in the detector each time. That is a testable claim, and I want to be clear about how good it was. It may be the cleanest prediction modern physics has ever handed us. We probably walked straight into it. Specific, numbered, losable. So how do you detect a handful of flashes a year? What does a machine like that require? And where on this planet does it have to stand? It requires us to leave the surface of this planet, and that sounds practical until you look at the reason. Our problem is noise, and I mean that in the physical sense. Cosmic radiation pours onto this planet constantly. Every particle in that shower can produce exactly the kind of flash in a detector that we are hunting for. Do you see the trap forming? On the surface, an instrument registers millions of false signals for every real one it might see in a year of running. Millions of them, against one. That was our starting position. So we went down into the rock, as far from that incoming radiation as we could physically get. The largest of these instruments now sit in old mines and under mountains. Gran Sasso in Italy lies beneath 1.5 kilometers of rock, which absorbs almost every incoming particle of cosmic radiation. Snowlab in Canada sits 2 kilometers down, inside a working nickel mine. That depth cuts the cosmic ray flux reaching our detectors by a factor of around 50 million. 50 million, and all of that just to hear one flash a year. And rock alone turned out not to be enough for us. The steel in the housing has to be old steel, smelted before 1945. Every batch poured since carries traces of radioactive fallout. Think what that means. We needed metal poured before we began contaminating this world with radiation of our own. Our tanks hold liquid xenon, purified far beyond anything else in industry. Around them we place further tanks of water, shielding the shielding, catching stray radiation the rock allowed through. Think about a house where you are trying to hear a heartbeat through a wall. First your television goes off. Then the fridge is unplugged, the traffic blocked out, the floorboards packed. Each step makes sense on its own. But stand back and look at what your house has become. It is not a room anymore. It is a sealed chamber whose entire design is the removal of the world, built by people who no longer live in it. That is probably what these places are, and I do not think we ever quite said it aloud. We did not add sensitivity so much as subtract everything else. We buried the detectors a mile underground, not to keep the signal in, to keep the world out. We had to hide from reality in order to hear it. So we built the quietest rooms on this planet. What came back out of them? What did all that silence buy us? Nothing came back out of those detectors, and that is the entire result of the exercise. It has been our result for 40 years of running these detectors. I want you to sit on that word, because after all this, we have earned the right to be shocked by it. Our first serious underground searches began in the mid-1980s, with equipment that looks naive now. Since then, the sensitivity of our instruments has improved by 6 orders of magnitude. That is a factor of 1 million in raw detector performance. Each generation of detector was larger, colder, cleaner, and quieter than the one before it. Every one of them was built by people who fully expected to be the ones who finally detected the particle. None of them were. Not a single one of them. 2 of them, XENO, NNT, and LZ, run now with tons of liquid xenon apiece. They are probably the most sensitive detectors we have ever built for any purpose. Their results keep arriving in exactly the same shape as every result before them. Year after year, run after run. No excess, no signal, nothing at all. Think about looking for your keys in your own house. You check the kitchen and they are not there. Your search narrows and you feel better, because the keys must now be somewhere else in the house. We check the hall, and then the bedroom, and then the car sitting outside. Each empty room feels like progress, right up until the moment you have checked every room in that house. Then, that emptiness stops being progress. It becomes a question about whether the keys were ever in your house, and whether you understood the problem when you started looking. We are near that point now, and I want to be precise about why. The remaining parameter space is closing fast, and beneath it lies a hard physical floor we cannot dig through. Solar neutrinos strike our detectors in a way that probably looks identical to the signal we want. Identical to us. Same energy. Same flash of light. Once we reach that neutrino floor, the search does not fail. It simply stops being possible for us to run at all. 40 years. Billions of dollars. The most sensitive instruments our species has ever built. And the answer keeps coming back the same. Not here, not this. Look again. So what do we do with a measurement that only says no? Is the room actually empty? Or were we simply wrong about the keys from the first day, in a way no detector can tell us? At this point, you should be pushing back. I want to give the objection its full weight, because it is a good one, and I have never found it easy to answer. If we invent a substance nobody can find, and then fail for 40 years, maybe our substance is the mistake. Does that sound reasonable to you? It should. Maybe there is no missing matter out there at all. Maybe our law of gravity is simply wrong at very low accelerations, out where almost nothing pulls on anything. And that is not a fringe position we can dismiss. Mordechai Milgrom proposed exactly this in 1983, and his modified law does something quietly impressive with our data. Hand it the visible matter in a spiral galaxy, and it predicts the rotation curve, arguably better than dark matter does. No halo of dark matter required anywhere. One adjustment to our physics, and dozens of galaxies fall into line. That is a real achievement, and we should sit with it before we start arguing. So the objection is serious, and nobody should wave it away. Here is where it runs into trouble. The modified law works on individual galaxies and struggles almost everywhere else. It probably does not account for the way our clusters of galaxies hold together. It cannot explain those two clusters that pass through each other, where the mass sailed on and the visible matter stalled behind. And it does not reproduce the pattern we measured in the background radiation. That pattern matches a universe containing cold, invisible matter to extraordinary precision. But notice the assumption hiding underneath our whole argument. We're being offered a choice between unseen material and a broken law, as though one of them is the comfortable option. Look at what a modified law of gravity would actually be, once you strip the label off it. An invisible adjustment to how everything moves. Present everywhere. Never seen, never held. Detectable only through the same measurements that handed us the problem in the first place. We cannot observe that directly either. We can only infer it exactly the way we inferred the matter. So both of our roads lead us to the same place. Whichever answer turns out to be right, whatever runs this universe stays out of your reach and mine. Is that a coincidence? Or is it simply the shape of our situation, showing up twice? So let us close this ledger and be honest about where we now stand. I think the shape of it matters more than the answer, and I want to lay the shape out plainly. We measured this mass 3 separate ways. Orbital velocity inside clusters of galaxies. Light bent around mass on its way to our telescopes. The pattern frozen into the background radiation of the early universe. 3 methods, built on different physics, run by different people, using different instruments across 90 years. Why would 3 unrelated measurements, taken decades apart, converge on the same wrong number? Every one of those 3 independent measurements agrees with the other 2 about the number. And that is the part which will not go away. It does not soften, it does not shrink, it has never moved. So this is probably not a rounding error, and not an artifact of one bad night at a telescope. It carries mass, it sits in every galaxy, and it shapes every structure we live inside. It is the reason our own galaxy exists in a form capable of holding us at all. And every attempt we have made to touch a single particle of it, directly, has come back empty. Does that combination sound stable to you? Think about a room where you can feel somebody standing just behind you. The floorboards take weight. The air moves. The temperature drops. Every measurement your body can take says a person is standing there. Then you turn on the light, and the room is empty. Nothing is standing there. And not one of the readings changes. Most people in that room would decide the equipment was broken. But what if that equipment is the only thing telling the truth all evening? That is our position now, and it carries a strange property that nobody planned or wanted. As we improved our instruments, generation after generation, the range where this material could hide shrank steadily, and the material stayed exactly 1 step outside it. Not once, not twice, every single time. Every time we make the machine quieter, the thing we are hunting gets quieter too, as if it is stepping back at exactly our speed. And this matter was only 27% of our problem. A larger share of the mass and energy is still waiting, and that one does not simply sit there refusing contact. It acts on everything you can see. In the late 1990s, two teams of astronomers set out to measure how fast the expansion of the universe was slowing down. Notice our wording there. Not whether it was slowing, how fast. We were all confident about the direction of the answer. The universe had been expanding since the beginning, and every scrap of mass inside it pulls inward, so the expansion had to be losing velocity. Our only open question was whether gravity would eventually win and pull everything back together. The alternative was that we coast outward forever, decelerating but never quite stopping. The two teams were competing with each other, which matters here. One of them was led by Saul Perlmutter in Berkeley, the other by Brian Schmidt and Adam Rees. Both used the same method. Both of them expected a number with a minus sign in front of it, and I want you to hold on to that expectation. Think about throwing a ball straight up out of your hand. You do not need any physics to know what happens next. It rises, it decelerates, it stops, it comes back down to you. We all learn this before we can read, and none of us has ever needed to check it. The ball is not deciding anything. Gravity pulls on it, and gravity works in one direction only. Does anything in your life contradict that? Now imagine we throw that same ball, and it rises, and then it speeds up. Not blown upward by wind. Not thrown harder than we thought. It accelerates away from us and keeps accelerating, and the harder we look, the more certain the measurement becomes. That acceleration is what we found. That is what came back to us in 1998, and I still find it hard to state calmly. Both teams. Same answer. Nobody wanted it. Each group spent months hunting through their own work for the error because the result was easier to blame on a mistake than to accept. Neither of them found one, and I think that is the honest part of this story. Then they found each other, and the two independent measurements matched. So the expansion of the universe is not decelerating at all. The expansion has probably been accelerating for roughly 5 billion years, and something out there is doing the pushing. So how do we measure the expansion of an entire universe from one small planet? What did we use as a ruler, and how far can you trust it? We use exploding stars as a ruler. I want to slow down on that because the trick behind it is where all the trust in this act gets deposited. Measuring how fast a distant galaxy moves away from us is the easy half. Its light arrives stretched toward the red end of the spectrum. The size of that redshift gives us the velocity directly. How would you get the other half? Any decent telescope can do it. The hard half is distance because nothing in the sky arrives with a label on it telling us how far it traveled. So we need what we call a standard candle, an object whose true brightness we already know before we ever point a telescope at it. If we know how bright something truly is, and we measure how bright it looks from here, that difference hands us the distance immediately. Nothing else is needed. No travel, no parallax, only the gap between two numbers. That is the whole method, and it probably sounds too simple to carry the weight we are about to put on it. One kind of star obliges us here. A white dwarf sitting beside a companion pulls matter off it, slowly, across enormous stretches of time. It gains mass steadily until it crosses a threshold, and at that exact threshold, the star detonates. That threshold is a number set by physics. It is the same number everywhere in the universe. So every one of these detonations releases close to the same energy as all the others. Same fuse, same limit, same output, every single time. Think about a long street where every lamp holds an identical bulb. You cannot walk that street to measure it, but you can stand at one end and look down it. The near lamps are bright and the far ones are dim, and that dimming tells you how far away each lamp stands. It works perfectly, and it works only because the bulbs are identical. Now notice what we are trusting here. We can walk over to the nearby lamps and open them and check. We cannot open the ones at the far end, and those are the entire point of the exercise. Do you see where the weight sits? We are assuming the bulbs stayed identical across billions of years. I think that single assumption may be doing more work than anything else in modern cosmology. So we pointed this ruler at the deep sky and read what it told us, what came back, and what was left to check it against. The distant supernovae came back dimmer than they should have been, not by much, but consistently, across dozens of them, in both teams, in every single batch we measured. Dimmer means further away, and further away than a decelerating universe permits under our own gravity. So in the billions of years since those stars detonated, the space between them and us opened faster than anyone had budgeted for. Do you see what that forces on us? Our ruler was built from nothing except the physics of a detonating white dwarf, and every reading it gave us said the expansion had gained velocity. Not held steady, not eased off, gained. Think about following a car down a long straight road at night. You watch the tail lights and you can feel the distance between the two of you. If the driver brakes, the lights swell. If the driver holds steady, so do they. You read that language without thinking about it. Now the lights start shrinking. They shrink faster every minute and there is no engine sound, no exhaust, nothing anyone can point at. The first instinct is to check the speedometer. The second is to wonder about our eyes. The last one, and the one we resist longest, is that the road itself is getting longer underneath us. That is what all of us were looking at, and I do not think anybody was ready for it. The number was not small. It changed the ending of every galaxy and every particle we know about. That acceleration has been running for roughly 5 billion years now, and I want to place the number carefully for you. Before that, gravity was still winning, and the expansion was decelerating exactly as any of us would have predicted. Then, the balance tipped. It tipped inside a universe already old, already full of galaxies, already producing planets. It tipped while our own planet was forming out of dust. We gave the cause a name, mostly because we had to write something on the axis of a graph. We called it dark energy, and that name probably describes our own ignorance rather than anything real about the thing itself. The universe is not simply expanding, it is accelerating. Something is pulling it apart, and it has been winning for 5 billion years. So what does something have to be in order to do that to us? What kind of thing gets stronger the more it works? Whatever is doing this to us has one property that separates it from every other thing we have ever measured. It does not thin out. I had to sit with that sentence for a long time before it landed, and I am still not sure it has. Take the ordinary matter that we are all made of first. Let the universe double in size and we find the same atoms spread through 8 times the volume. The density drops by a factor of 8. Radiation thins even faster than that, because we watch the wavelengths stretch as well. Every single thing we have ever measured in a laboratory behaves this way. More room, less of it per cubic meter. That is what dilution means to us, and nothing in your experience escapes it. This does not dilute. As far as we can measure, the density of dark energy stays flat while the volume around it grows. Flat. Not slowly falling. Flat forever. Think about pouring a bottle of ink into the bath you fill for yourself. The water turns grey. Keep adding water and that grey fades, because there is only so much ink in the bottle and it has further to spread. Now imagine you double the water and the shade never changes at all. Not slightly weaker anywhere. Identical. There is only one way any of us can read that result. The water is arriving with ink already in it. So that is our situation, and I want to be careful with it. Every new cubic meter of space appears to arrive carrying its own share of this energy. So the total amount of it grows as our universe grows, which is the opposite of everything you know about how a supply behaves. It does not run down. It compounds. It never stops. The density itself is almost nothing, and here is where we stop feeling threatened by it. Roughly the mass of a few atoms of hydrogen in every cubic meter of space, possibly less. Inside the whole volume of your own body, there is less than a single atom of it. That is why we will never feel it, and why no laboratory on this planet can isolate a sample of it. But space is enormous, and space is winning. Add it up across the whole volume, and it outweighs every scrap of matter in existence, visible and invisible together. Does something that faint deserve to be the majority? So how much has it already taken away from us? What does that count look like once we actually run it? The count exists, and I think it is one of the strangest numbers we have. It only moves in one direction, and it never stops moving. Would you want to know your own version of it? Start with what we can actually see from here. The observable universe probably holds somewhere around 2 trillion galaxies. That is our inventory of everything, and I think most of us hear a number like that as an inheritance. Now ask a different question with me. Not how many can we see? How many of them could we ever reach if we left tomorrow at light speed and never once slowed down? The answer is a few percent of them, and that fraction has been shrinking every second since the acceleration of the expansion began. Everything else is already gone. Not distant, not difficult, gone. Beyond a certain distance from us, the space between our galaxy and another expands faster than light can cross it. Not because the galaxy travels faster than light, nothing travels faster than light. The space in between is simply being added faster than light can eat into the gap. A photon leaving that galaxy right now will never arrive here. One leaving us will never arrive there. Nothing you build changes that. No physics we discover changes it. Think about walking towards somebody along one of those airport walkways that runs the wrong way. We walk faster and we gain on them, exactly as expected. Then somebody starts adding new sections into the middle of that walkway. The more distance already lies between you, the more sections appear. Past some separation, you can run flat out and still lose ground. Nothing about the other person changed. Nothing about your legs changed. The floor between you began manufacturing itself out of nothing. That boundary is real, and we can calculate exactly where it sits from here. Galaxies cross it constantly, while you sit here. Once one of them has crossed, it lies beyond any influence we could ever have on it, forever. We still receive its old light for a long while, so the galaxy looks present to us. It is not present. We are watching a recording of something we have already lost, and the recording will run for billions of years before it fades. So, what happens once every galaxy out there has crossed? What does the sky look like to whoever is left standing under it? Now, follow the logic forward with me, because this is where it stops being astronomy and starts being about the matter you are made of. Everything holding you together is a balance, and we can write both sides of that balance down. Gravity holds a galaxy together against the expansion of space and wins easily, because on that scale, gravity is overwhelming. It is not close, not even slightly, not a contest. The same is true of our solar system, of this planet, of your body, and of every atom inside it. At every level of structure, something local pulls harder than space pushes. That is probably why anything exists in a stable form at all. But every one of those balances depends on a single number, and that number is how strongly this energy pushes. If that push stays constant, we get a slow cold emptying out, and every structure we care about survives inside it. But if the push strengthens over time, the balance fails from the top downward. Some of our models allow exactly that. Do you want to know the order it happens in? Clusters of galaxies separate first, then galaxies come apart, then solar systems come apart, then planets, then the molecules in your hand, then the atoms holding those molecules in shape. Think about a sheet of cloth that we pull steadily from both edges. The seam gives first, because it is the weakest joint anywhere in the material. Then the weave opens under our hands, then the individual threads pull apart, and at that point, no smaller structure remains to fail. We tend to assume the tearing stops somewhere, and that our material has a flaw beneath it. It does not. There is only the level where the force has not yet grown strong enough. The timing in these models is not next week. It runs to tens of billions of years, and I want to be honest with you that we have not confirmed this branch. It may never happen at all, but we have already demonstrated the principle itself at the largest scale we can measure. The push is real. We watch it winning against gravity across the widest structures in existence, and it has been gaining for 5 billion years. It will not stop at galaxies. Given enough time, it comes for atoms. So which branch are we standing on right now? Is that number holding steady? Or has it already started moving on us? For 25 years, we assumed it was holding steady, because that was the simplest thing our data allowed. Simplest is not the same as true, and you should keep those apart. The simplest version of the physics treats dark energy as a constant, unchanging in time and identical everywhere in the universe. A fixed property of empty space, the same today, the same everywhere. Einstein had already written a term like that into his equations in 1917, and then pulled it out again. We put it back, gave it a value, and everything fitted. Then we started measuring the thing properly, and our simplest answer began to wobble. The Dark Energy Spectroscopic Instrument sits on a telescope in Arizona, and it maps the positions of millions of galaxies at once. Do you know what that lets us do? By comparing how structure clumped at different eras, we can track how the push behaved over time. We stop assuming and start watching. Our results, released across 2024 and 2025, hint at something none of us ordered. The strength of dark energy may not be a constant at all. The shape of the signal points towards something changing across cosmic time. Stronger before, weaker now, not by much. Enough to matter. I want to be careful with you here because this one is live and unsettled, and I would rather understate it. The signal has not reached the level we call a discovery, and it might dissolve as more data arrives. Several independent groups are working through it right now. It is an artifact of how our measurements combine, unless it is not. Anybody telling you the constant has been overturned is running well ahead of what we actually have in hand. So notice what we are arguing about now, not whether an invisible thing runs the expansion of everything. That part is settled, and nobody is fighting it. Our argument is only over whether the invisible thing is steady or changing. Think about a tenant who has never once met the landlord. The rent arrives, the roof gets fixed, and the rules apply to everybody in the building. Then one year the rent moves, and our tenant realizes he cannot ask why. He has no idea who sets it. He never did. He simply lived there and paid. So what would it feel like to live inside all of that and never notice? What would a whole civilization have to miss? Run our clock forward and something happens to the sky that nobody plans for. I think it is the part of this act that we should not skip. Give us 100 billion years. Our own galaxy and Andromeda will probably have merged into one large island of stars. Every other galaxy we can currently see will have crossed the horizon and gone beyond any telescope. All 2 trillion of them. The background radiation left over from our beginning will have stretched so far toward the red that no instrument can register it. The sky will hold stars, and beyond those stars, nothing measurable at all. Can you picture what that does to a science we would call rigorous? Now, let us put an astronomer inside that sky. A careful one, with far better equipment than anything we have. She measures the stars around her and finds they are not receding, because gravity binds them to her the way it binds us to ours. She looks past them and finds no other galaxies, so nothing exists whose redshift could reveal an expansion. She finds no background radiation, so nothing in her data hints at a beginning. Every measurement she takes is as correct as anything we take. Every instrument she builds works perfectly. Her arithmetic is clean. And the universe she describes to her students is one galaxy, unchanging, sitting in permanent darkness, with no history and no edge. Think about a village at the bottom of a valley where the fog has never once lifted. Generations of them map that valley precisely. Every field measured, every stream charted, every slope surveyed down to the meter. Nobody there is lazy, and nobody is being fooled by anyone. You would trust their measurements. Your maps of that valley would not be approximations either. They are exact, and we would recognize the work as good. And nothing about an exact map tells you where its edges are, or that anything was ever on the far side of them. That is what we keep missing. So the cosmology she leaves behind will not be sloppy. It will be rigorous, self-consistent, and supported by every measurement she can reach. One day, the sky will be empty. Whoever is left will look up, measure everything correctly, and conclude that they live in a small static universe with nothing beyond it, every instrument will agree, every instrument will be wrong. So what separates her from you and me? What are we standing on that she is not? Nothing separates her from us except position on a clock. And I would rather that were not the case. Is she making an error any of us would catch? She's doing everything we do, with better instruments and cleaner data, inside a universe that quietly removed her ability to check. Her cosmological horizon has closed completely, while ours is still closing at a rate we can measure and write down. Not a different physics, not a different mistake, a different hour, and some of it has probably already gone. That is not a prediction. Galaxies have been crossing our own horizon for billions of years, and everything past that boundary now sits outside any measurement anyone will ever make. Not hard to reach, not merely distant, outside every instrument we could ever build for the job. A telescope does not show us the whole universe. It shows the mass and radiation that have not left yet, and I find that a hard sentence to write. There is a second wall standing behind us in time. For its first few 100,000 years, the universe was opaque to radiation, so no photon from before that era ever reaches our detectors. That radiation is not faint, it is absent entirely. So our entire record of the beginning starts at the moment that fog cleared. Not at the beginning, at the clearing. Think about walking into a long conversation exactly halfway through it. Within a minute, you can follow it. Within 5, you're contributing, and everything anybody says makes sense. Does anything feel absent? Nothing feels missing because the part you missed left no gap behind it. It left a starting point instead, with no seam in it. That is our trap. Fluency feels exactly like understanding from the inside, and no signal in the room tells you the room began earlier. So we have a sky that is emptying, a wall we probably cannot see behind, and instruments that cannot report what they never received. How much of our physics rests on a sample of the universe that we did not choose and cannot audit? And that is the part you should sit with. Because nothing in that scenario tells them it happened. So how would you know it has not already happened to us? We have been talking about things that hide by leaving. There is one more, and it does the opposite. It never left. It is sitting in the vacuum between your hands. Take a box and empty it out. And I mean properly. Pump out the air until almost no molecules remain inside. Shield it so no light of any wavelength gets in. Cool the walls toward absolute zero so nothing radiates at all. Take out every single particle of matter that we know how to name. Now hold that box in your head for a moment. What is left inside that box? Take a moment with it. Because the answer is probably not what you would guess. And it is not what anybody guessed for 2,000 years. The obvious answer is nothing. I think that word deserves far more suspicion than any of us tend to give it. We use it constantly. We have never once tested it. Not properly. Think about emptying a glass of water. You tip it over the sink, shake it out, dry it with a cloth, and now the glass is empty. Except that it is full of air. So you pump that air out too, and now the glass holds a vacuum. Except that this vacuum has radiation crossing it, so you shield the glass. Notice what keeps happening to us here. Emptying something never once arrives at nothing. It arrives at whatever was underneath the last thing taken out. We have been swapping one content for another our entire lives, and then calling the final swap an empty container. You do it daily. So do I. Nobody notices. Here is where it stops being a word game for us. When we strip out everything we can name, our box is not quiet. Physics says our box cannot be quiet, and the reason has nothing to do with the quality of the pump. The best vacuum we can build in a laboratory still holds a few particles per cubic centimeter. At sea level, that same volume holds roughly 10 billion of them. Interstellar space does better than any equipment we own, and it is possibly the emptiest place we can point at. But even a perfect vacuum, with every last particle gone, is predicted to be full of something no pump can reach. It is not sitting inside the space. It is a property of the space, in the same way that hardness is a property of iron, rather than a thing inside iron. And that property carries energy. The amount can be calculated. That calculation hands us the worst answer in the history of physics. And we will come to it. So, what is actually happening inside your box right now? And why can nothing not simply be nothing? The reason your box cannot be quiet comes from a rule we stumbled into while studying something else entirely. I still think it is the strangest law we have. In quantum mechanics, we run into a hard limit on how precisely two linked quantities can be pinned down at the same moment. Position and momentum is the famous pair. Do you know what happens when we apply that to empty space? The more exactly we fix one, the less exactly the other can be defined. This is not a problem with our instruments or our patience. It is a statement about what it even means for a quantity to have a value at all. Now apply that rule to a field rather than to a particle, and watch what it does to the inside of your empty box. For your box to be truly empty, every field crossing it needs a value of exactly 0. It also needs a rate of change of exactly 0, in that same instant. Two linked quantities, both pinned perfectly at once. That is exactly what our rule forbids. So the fields probably cannot sit still anywhere. They are not permitted to. The quantum fields fluctuate around 0, always, everywhere, whether or not any of us is there to notice. That fluctuation may well be the most common event anywhere in existence. Think about the surface of the sea on a completely calm day. No wind at all, no storm, nothing driving the water. We call that calm, and from the deck of a boat it looks flat to us. It is never once flat. There is always a slow swell moving under the hull, because water in a gravitational field cannot hold a perfectly level surface for us. Calm does not mean motionless. It means the smallest motion the situation allows, and we have all been reading that word wrong. So that is what a vacuum actually is for us, not the absence of a field. The lowest energy state a quantum field is permitted to occupy, and that state is not 0. We call this 0-point energy, and I think the name is more honest than most in physics. 0 point means our temperature has gone as low as any temperature can go, and the energy is still sitting right there. It does not leave. It cannot be made to leave. So your box is completely full, which raises the obvious question for all of us. If it is full, why does nobody feel it? And what would it take for us to push against something like that? None of us has to take that on faith, because we found a way to push against the vacuum and measure what pushed back. Casimir worked it out in 1948, and the setup he proposed is almost insultingly simple. We take two metal plates, no charge on either of them, no magnets, nothing clever anywhere in the apparatus. Do you see what is missing from that list? Every single force you have ever heard of. Hold them parallel inside a vacuum, very close together, and watch what happens to them. Here is the reasoning we use. The quantum fields filling that vacuum fluctuate at every possible wavelength and frequency. Outside our plates, every wavelength has room to exist. Between the plates, only certain wavelengths fit, because the gap is narrow and the rest of them simply cannot exist in there at all. So more fluctuation presses on them from outside than from within, and the plates get pushed together by that imbalance. We add nothing. We simply exclude something. The push follows on its own. Think about standing in a packed crowd with somebody a single step in front of you. Nobody grabs either of you. Nobody pulls. Nobody has to. But the crowd behind you is larger than the sliver of crowd between the two of you. So you drift together, whether either of you wants it or not. Ask what did the pulling, and we have no answer, because nothing pulled at all. The gap between you was simply emptier than the space around it, and emptiness turned out to carry a weight of its own. Steve Lamoureux measured the effect properly in 1997, using a torsion pendulum and a great deal of patience. The force is real. It probably matches our prediction to within a few %, and we have reproduced the result many times since. The scale of it is what stays with me, and I keep going back to the number. At a separation of around 10 nanometers, the pressure exerted by empty space on those plates approaches 1 atmosphere. That is possibly the weight of the whole column of air above your head, produced for us by the absence of everything. So we pushed on nothing, and nothing pushed back, hard. with a number attached to it, which means we can now ask a far harder question about that energy. How much energy sits in there in total, and what happens to us when we finally do that arithmetic? So we went ahead and did the arithmetic, and I want you to watch what it returns to us. This is where it stops being a laboratory curiosity and becomes the most uncomfortable number our species has ever produced. We have two independent ways to get at the energy of empty space, and normally that would be very good news. The first road is theoretical, and it starts from the physics we just described. Quantum field theory tells us how the fields fluctuate, so we add up the energy contributions from every wavelength and arrive at a density. The second road is observational, and it starts from the sky above your head rather than from any equation. That vacuum energy pushes space apart, and we have been measuring the acceleration of the expansion since 1998. So the sky itself hands us a value. Two independent roads to the same physical quantity. This is exactly the situation we are supposed to love, because agreement between the two would confirm everything sitting underneath both of them. They do not agree, not roughly, not within a factor of 10, nowhere close to it. Our theoretical number comes out larger than the measured one by something in the region of 10 raised to the power of 120. A 1, followed by 120 zeros, standing between our best theory and our best measurement. Think about a builder giving you a quote for a garden wall. He quotes you £400 for the work. The bill arrives at 410 and you shrug, because estimates always drift a little. Now imagine that the bill arrives for more money than exists anywhere on this planet. Then more than that again. The builder is not joking, and the wall is standing there in front of you exactly as described. And at that point, our argument is no longer about the price at all. Do you see how the difference changes? Something is wrong with the entire idea of what a quotation is. We usually call this the vacuum catastrophe, and I think that word is doing a great deal of gentle work on our behalf. Empty space is not empty, it is boiling. And our best theory predicts the temperature of that boiling with an error of 120 zeros. So, how wrong is that number really? Is there anything in your experience that stands next to a number like that? Numbers that large stop being numbers and turn into noise. So let us put this one somewhere you can stand next to it. I have never found a comparison that fully works. I doubt one exists, but this gets close enough to feel. Start with something we already agree is enormous. Can you actually picture a count of this size? Count every atom in every star, every planet, and every cloud of gas across the observable universe. Every atom held inside all 2 trillion galaxies we can observe from here. The answer we give is around 10 raised to the power of 80. That is probably the largest honest count our species has ever produced, and it covers every scrap of matter in existence. Every atom, everywhere, all of it. Now hold our error up next to that count. Our theory predicts one vacuum energy. The sky measures another. The gap between them runs to 10 raised to the power of 120. Now divide one by the other and look at what we are left holding in our hands. Our mistake is not slightly larger than the number of atoms in existence. It is that entire count of atoms, multiplied again by 10,000 trillion. Think about pacing out a room to buy a carpet for it. We walk the length of it, write down 4 meters, and the answer is wrong. Not by a handspan, not by the width of a single doorway. Your answer is out by a distance that would cross this galaxy and keep going. Nobody hearing that would bother checking the walking, or the arithmetic, or the pencil. We would ask whether you and that room are even the same kind of thing. We would ask whether the word meter still means what you assumed. That is our position with the energy of the vacuum, and the phrase we use for it is a quiet scandal. We say the theory requires fine-tuning. What that means in practice is that the number must be cancelled to more than 100 decimal places by something none of us has identified. Otherwise, no matter exists anywhere at all. Not one atom of it. Not roughly cancelled. Not mostly. 120 digits of cancellation. If any one of those digits were off, we would have no galaxies, no chemistry, and nobody here to notice the difference. So how does any theory survive an error on that scale? Why is any of us still building on top of it? It survives because that same theory is the most accurate thing our species has ever written down. I want us to hold both of those facts at once, because I think the discomfort lives in the gap between them. Quantum field theory does not only hand us an energy density for the vacuum of empty space, it predicts how the magnetic moment of an electron behaves inside a magnetic field, and that particle quantity can be measured with extraordinary care. That measurement has been made repeatedly in different laboratories with different equipment. Theory and experiment probably agree on that energy to something like 12 decimal places. 12 decimal places of agreement between our prediction and our measurement of that energy. That is roughly like predicting the distance from London to New York and being wrong by less than the width of a human hair. Do you know of anything else that does that? Nothing else built by anybody comes close to that. Not our models of the weather. Not our chemistry of matter. Not one branch of the engineering that we practice on this planet. So when physicists call this the best theory, nobody is being polite. The claim is meant in the narrow, measurable, unarguable sense. Every prediction of the theory that we can test, it gets right, over and over again. The precision has no rival in any other field of measurement. Think about a builder whose walls are perfectly straight. Every measurement checks out to the millimeter. Every door hangs true. Every joint is exact. And you have watched this man work for a century. Then he hands over the invoice, and the total on that page is a number carrying 120 digits. You cannot dismiss the man. You have his walls holding up your roof. You are standing inside those walls right now. But you cannot pay that bill either, and you cannot pretend the paper is not in your hand. And that is exactly where all of us are standing today, inside this physics. Our theory is right about every quantity we can reach and measure, and catastrophically wrong about the one vacuum energy we cannot. That is not a mistake. That is the largest wrong answer in the history of human thought, and we are still building on the theory that produced it. So what does that tell us about the theory itself? Or is it telling us something else entirely, about the boundary of what we are able to reach? The obvious response is to throw the theory out, and I understand that instinct completely. But watch what happens to us when we actually try it. If we discard quantum field theory, we discard those 12 decimal places along with it. Does that trade look good to you? We lose every prediction that works, all the technology built on those predictions, and the entire foundation of modern particle physics. Nobody has an alternative that keeps the accuracy and repairs the vacuum energy at the same time. So, the honest position is probably not that our theory is broken. It is that the theory is doing something considerably stranger. Look at where it succeeds and where it fails. It succeeds everywhere we can interact with matter and radiation. It fails at the one quantity we cannot touch, cannot isolate, and cannot put on a bench. Think about a shop scale rated to 10 kilograms of mass and no more. Weigh a bag of flour on it, and your reading is exact to the gram. Weigh a crate, and it is exact again. You would trust a scale like that with anything. Now, drive a car up onto that same platform. The scale does not break, and it does not refuse to do the job. It gives us a reading, and the reading is exactly as detailed and as confident as every correct one before it. Clean, confident, precise, and completely wrong. Nothing on that display warns you that the range has ended. The scale has no way to tell any of us it left the territory it was built for. That is the pattern, and by my count, we have now watched it happen 4 separate times in a row. The eye reports honestly and cannot report radiation that never reached it. The detector counts honestly and cannot count a particle that never interacts. Our standard candle is calibrated honestly at the near end. It cannot be checked at the far end, which is the end that matters. And now, the best theory any of us has returns a number with total confidence, from outside the range where anybody can check it. So, the failure we are looking at is probably not random at all. It sits in exactly the same place every single time, at the edge of what we can touch. Which raises the question we have been avoiding all along. What if the vacuum itself is not what we assume it is? What if the vacuum is not even a stable state of matter? We have been treating the vacuum as the floor underneath everything, the bottom, the state that all matter settles into when there is nothing left to give up. How would we ever check that? But do we actually know that? There is a reason to think our assumption is wrong, and it comes straight out of the Higgs field. In 2012, we measured the mass of the Higgs particle at the Large Hadron Collider. That number went into an equation alongside the mass of the top quark. Together, those two masses set the shape of the field that fills all of space. That shape decides whether our vacuum is the lowest energy point in existence, or merely a dip on the way further down. The values we measured put us close to a boundary, not comfortably inside it, close to the line, on the wrong side of it for all we know. Think about a bottle of water left in a very cold freezer. You take it out and the water is still liquid, sitting well below freezing point, perfectly calm in your hand. Nothing about that bottle looks wrong. It looks perfectly stable to us, and in a sense it is. Then, you knock that bottle against the counter. The whole thing turns to ice in about a second, end to end, faster than you can pull your hand away. It was never stable at all. It was waiting, and nothing any of us could have measured from the outside would have told us which of those two it was. So if our own vacuum is that bottle, then somewhere out in the universe the physics can tip. Not gradually, not with any warning. One region flips over into the true lowest state. The boundary of that region expands outward at close to light speed, and inside it every constant of physics takes a different value. Atoms of the kind we are made from would not hold together in there. Neither would we. I want to be very clear with you that this is a calculation, not an observation of anything. The timescales involved run far longer than the current age of the universe by an absurd margin, and our measurement carries real uncertainty inside it. Does that settle you? It has never once settled me. If the vacuum is not the lowest state, then somewhere a bubble may already be expanding at the speed of light, rewriting the rules as it goes. You would not see it approach. There would be no approach. There would only be after. So let us close this out and say plainly what the vacuum has turned out to be for us. I think it is worth laying all 4 steps down side by side. We emptied a box of all its matter and radiation as far as anybody knows how, and it was not empty. We put 2 uncharged metal plates inside it. That emptiness pushed them together with roughly the weight of an atmosphere. No force involved, no matter between them at all. Then we calculated how much energy was sitting in there and produced the largest wrong answer in the history of human thought. And when we checked whether that state was even the bottom, our equations came back uncertain about the answer. Do you see the shape of that sequence? Every single step took something away from us and gave nothing back. Now notice what has quietly happened to one of our words. We started with the vacuum as a setting. Somewhere along the way, it became a participant. Think about the floor of the house you're sitting in right now. Have you ever once thought about it? Almost certainly not, and there is no reason on earth why you should have. You walk on it, you put furniture on it, and you assume it is the thing everything else happens on top of. The floor is not part of your day. It is where the day occurs. Now imagine a morning when that floor moves, not by much, just enough that you feel it through your knees. From that moment, the floor is no longer the setting. It is a participant. It always was one. And the only reason any of us ever called it background is that it never once asked anything of us. That is what happened to empty space over the last century. It stopped being our container and became one of the contents, carrying an energy density and a measurable pressure of its own. And every hidden thing we have looked at so far has been an object of some kind. Mass we cannot see. Energy we cannot isolate in a laboratory. Quantum fields we cannot hold still. All of them are things that exist and refuse us any contact. So what could possibly be left? But there is one more kind of hiding, and it works differently from all of them. It does not hide by sitting far away from us And it does not hide by refusing to interact. It hides by not having decided what it is yet. And I do not know a stranger sentence anywhere in physics. Let us make an assumption for the next stretch and see where it carries us. I am not asking you to believe it yet. Suppose some of what is hidden from us is not hidden at all. Suppose that part of physical reality has simply not settled on an answer yet. That sounds like wordplay, so let us make it concrete with an ordinary coin and nothing else. We flip one and catch it flat under a palm without looking. There is a face of that metal pointing up underneath the hand. Nobody knows which, but the coin has landed and the metal is resting flat against skin. Our ignorance is about us, not about the coin. Lift the hand and we learn a property that was already true before anybody looked. The coin decided its state. We only caught up. Now take that same piece of metal and spin it on the table instead. While it is spinning, is it heads or tails? Not unknown, not covered. There is genuinely no answer yet, and none of us would say the spinning coin is hiding one. It is simply not the kind of situation where that question has an answer. The situation only acquires an answer when the coin comes down onto the wood and the spin decays away. Two states of one object, and the difference between them may be the largest gap in modern physics. In the first case, a property of the particle exists, and we simply lack access to it. In the second case, there is no property yet for any observer to reach. Every intuition you own is built on that first picture. It is probably the deepest assumption any observer carries. Not knowing and not being decided feel identical from where we stand. In ordinary life, the two really are the same thing. Here is where it stops being a nice image. For a century, we have run experiments on particles. We were trying to find out which of those two pictures describes the matter and energy you are assembled from. Every atom of it, every particle. Which of them would you bet your matter on? For most of that century, we assumed the covered coin, and I think every physicist alive assumed it with us. Einstein assumed it. He fought hard for it. He lost. And every one of our particle experiments keeps coming back the other way. So, what exactly is undecided down there at the level of particles and atoms? And how much of the matter you are made of is still waiting? The experiment that settles this for us is old, cheap, and has been repeated in undergraduate laboratories for decades. I want us to walk through it slowly, because every step is ordinary until one of them is not. We cut two narrow slits in a card and send light through them onto a screen behind it. What appears is not two bright lines. We get a whole series of them, bright and dark alternating outward, which is what waves of any wavelength do whenever they overlap. Where two crests of the wavelength meet, we get brightness. Where a crest meets a trough, we get darkness. Nothing surprising in any of that. Every wave in your bathtub does the same thing. Now we slow the source down until it releases one single photon at a time, one particle of radiation with a gap between each. We watch each one land on the screen as a single dot, arriving at one place and nowhere else. Not a wave, not a smear. 1 point. And yet, as those dots accumulate over hours, they build the same stripe pattern we saw before. Every particle crossed alone, with nothing to overlap with, and the interference pattern still assembled itself out of them. Think about sorting letters into two chutes. Every letter goes down one chute or the other, and at the bottom we count what arrived in each tray. Open a second chute and more letters arrive, always. That is simply what opening a route means to us. Now imagine that opening the second chute causes fewer letters to land in a spot where the first chute alone had been delivering them. Not the same number. Fewer. You added a way in and the deliveries dropped. At that point, we are not looking at a sorting problem anymore. We are looking at something wrong with the word route. That is our result, and I have never seen anybody talk their way around it. It holds every single time. Then, we put a detector at the slits to see which one each particle actually uses. This is where your intuition should be winning. The detector works perfectly. It reports the path to us, reliably, on every single run. And the striped pattern disappears. Do you see what has to be explained here? Not a nudge, not a smudge. The entire pattern is gone. 2 plain bands appear, exactly as your intuition demanded from the start. So what did that detector actually do to the particle? And what is it about being watched that changes where a particle lands on a screen? Before we go further, I need to close a door, because this is the exact point where the subject usually gets stolen from us. The word watch does a great deal of damage to us here. It suggests a person, a pair of eyes, an act of attention. It suggests that our own awareness is doing something to the world. That is not what any of these experiments show. Do any of us need to be there at all? The honest answer took our field decades to accept, and it is worth stating as plainly as we can manage. Nobody has to be in the room, nobody has to be awake, nobody has to exist. The detector at the slits does its work whether or not anyone ever reads the output of it. It records the passage of a particle. That is the whole of what it does. It works if we lock the laboratory and walk away, and the results sit on a drive for a decade before somebody opens the file. So what matters here is not that somebody knew. What matters is that the information about the particle got out into the world. Think about a secret that you are keeping right now. We tend to feel it stops being a secret at the moment somebody reads it, but that is not the moment it changes. It changes when you write it down, because from that instant, the information exists somewhere outside your head. Whether anybody has read the page yet is a detail. The page is the event. The reader arrives later, and the reader was never the point of it. So that is what a measurement really amounts to in our physics. Not a mind arriving, a record forming. And the record we are talking about does not need a laboratory. We do not need equipment at all. One stray molecule of air bouncing off that particle carries away information about its path. That alone is enough to erase the whole pattern. This is why the effect is so hard for us to see in daily life. Every molecule of matter around you is constantly bumping into every other molecule. So the record gets written instantly, and the strangeness is buried under the noise of an ordinary room. So we can drop the mysticism from this entirely, and I would much rather we did. Our rule concerns physical interaction between particles, not attention. But if that is our rule, what exactly was the particle doing before any record of its path existed? And what was actually true about it? For 30 years, this looked to us like a question nobody could ever settle. Either a particle carries its properties in advance, and we simply cannot see them, or it carries nothing at all. Both pictures predicted the same laboratory results for us, so the argument stayed philosophical, and most people got tired of having it. Then, in 1964, a physicist named John Bell found a way to turn the whole thing into arithmetic. I think it is the cleverest move anybody has made in modern physics, and it works on counting alone. He stopped asking what a particle is, and we started counting how often 2 particles agree with each other. That is the whole trick, and I still find it hard to believe it works. You take a pair of photons created together, send them far apart, and then measure each particle separately. We do it thousands of times, varying the angle of each particle measurement, and we record how often those 2 answers match. Think about sending 2 people to opposite ends of the country, each carrying a sealed envelope of instructions. Would you need to read those envelopes to learn something about them? At the far end, each of them is asked one of 3 questions, chosen at random. Each of them answers yes or no according to the instructions they carry. Now here is the useful part, and it is why the idea works at all. We never open those envelopes. We simply count how often the 2 answers we receive happen to agree. And if those 2 are really carrying instructions written before they left, then a hard ceiling sits on the correlation between their answers. No set of instructions any of us could write will beat it. None. That ceiling is arithmetic, not physics. Bell derived exactly that ceiling for a pair of particles. If particles carry their properties in advance, and if no signal travels faster than light between them, then our measured correlations cannot exceed one specific number. And our quantum mechanics, the same theory that gave us 12 decimal places, predicts a number sitting above that ceiling, higher, impossible, and measurable in a laboratory. So your philosophy turned into a measurement. 2 answers, 1 number on a page, and probably no room left to argue about the quantum interpretation. All any of us had to do now was build the experiment. So what happened when we finally built it? And what would you have bet? Alain Aspect built the experiment in Paris in 1982, and I think you should know what he did to make it airtight. He also added something Bell had only been able to wish for. The obvious objection to any test like this is that the 2 ends might be communicating with each other. A signal passes from one detector to the other, carrying the angle we chose, and the correlation gets arranged in the ordinary way. That is likely what any of us would assume first. So Aspect made the choice of angle while our photons were already in flight, halfway across the laboratory. We switched it fast enough that no signal at light speed crossed the gap in time. Each end of the apparatus chose its question after the particles had already left. Neither end of our apparatus had any way to know what the other would ask. Do you see how tight that closes the room? Then we counted the agreements between our 2 particle detectors, thousands upon thousands of them. The number our detectors handed back sat above the ceiling that Bell had derived from pure arithmetic. Not marginally, not inside the bars, above it. Comfortably above it. Exactly where quantum mechanics said it would sit, and exactly where no set of pre-written instructions ever reaches. Think about our 2 people with the sealed envelopes again. Our 2 people come back from opposite ends of the country. We find that their answers agree with each other far more often than any set of written instructions could allow. Far more often, every run, every time, and now we have only 2 ways out of it, and I dislike both. Either those 2 were talking to each other across a distance no message crosses in the time available, or there were never any instructions in those envelopes at all. Those envelopes were empty when your 2 people left. The answers were decided at the far end, in the moment of asking, and not 1 instant before. Every loophole any of us raised has since been closed by somebody with better equipment. The cleanest tests we have were run in 2015, and the result did not move by anything. The Nobel followed in 2022. Reality does not appear to decide what it is until something looks. We have spent a century trying to prove that wrong. It keeps winning. So how far up the scale of matter and mass does this go? Does it stop somewhere before it reaches you? The Nobel Committee gave the prize for this in 2022. And I think it is worth being precise about what exactly they were rewarding. Not the strangeness itself. We had known about that for decades, and knowing it changed nothing. What John Clauser, Alain Aspect, and Anton Zeilinger did across 50 years was close our escape routes, one at a time, until we had none left. Clauser ran the first real version of Bell's test in 1972, and he got a violation straight away. Our objection was that his detectors were inefficient, and that they might have been sampling a biased subset of the particles. So we went away and built better detectors. Then Aspect switched the angles in flight, and removed any possibility that our 2 detectors were signaling to each other. So our objection moved to whether the switching itself was truly random. Zeilinger and others pushed the randomness further still, closing gap after gap in the equipment. Then, somebody had an idea that I still find unsettling to describe. Suppose we need randomness that could never have been coordinated with the particles. Where would any of us get hold of something like that? We take photons from 2 distant quasars, billions of light years apart, and let the arrival time of each photon choose our measurement angles. That radiation left before the Earth existed. So if some hidden arrangement is fixing our results, then it was set up long before this solar system formed, before the sun, before any of this. We ran it using photons that had been traveling since before the solar system condensed out of dust. The violation held. It did not shrink, it did not blur. It sat exactly where the theory put it. Think about an argument where you keep saying yes, but what about this? Each time the other person answers you, and the room gets a little smaller around you. Eventually you run out of objections altogether, and the room goes quiet. Now notice that running out of objections is not the same thing as being persuaded, and every one of us knows that difference from the inside. That gap is where we are all standing right now. We have no objection left to raise. We also have no picture at all of what is actually happening to the particles. So what does the past actually look like if nothing in it was decided? And when exactly did it become the past? John Wheeler asked the obvious follow-up question in 1978. The answer is probably the part of all this that I find hardest to hold in my head. His idea was simple enough. In the two-slit experiment, we decide in advance what to measure. You can ask for the path of the particle, or you can ask for the interference pattern, and the apparatus is set up before anything moves. What happens, he asked, if we wait until the particle has already gone through the slits, and only then decide? By then, the particle has committed itself, or has it committed anything? That particle either went one way or it went both ways. Whatever the particle did is finished and behind us, so a choice made afterwards should not matter to the outcome at all. We built the thing using detectors and switches fast enough to beat the particle down the apparatus, and our result comes out matching whatever we chose. Nothing lags behind. Nothing resists us. Nothing objects. Ask for the path and we get a clean path. Ask for the interference pattern and the pattern is there. Every time. Without exception. Whatever we choose. Think about walking down to a beach in the morning and finding footprints in the sand leading up to a house. You would conclude that somebody walked there during the night. Those prints are a record of a walk that happened, and nobody sane doubts it for a second. Now, imagine a beach where those prints appear only when you go looking for them. If instead you check whether the sand is smooth, then the sand turns out to be smooth, and there was no walk at all. Not erased, not hidden. There was simply no fact about that walk until somebody went and asked for one. Wheeler pushed the idea to the largest scale he could reach. Radiation from a distant quasar bends around a galaxy on its way to us, taking two possible routes around all that mass. We choose our measurement tonight. That journey took billions of years, and all of it was over long before we chose. We are not changing the past when we do this, and I want to be careful about that. There is no fact about the particle sitting in that past for us to change, which is worse. So a record forms at the moment we ask for it, which raises an obvious question about everything else we call history. How much of your own history is like that? The comforting reply to all of this is that it only applies to very small things, and I used to find that reply reassuring. Particles behave strangely, you and I behave normally, and somewhere in between there must be a boundary. So let us go looking for that boundary together. Where would you expect to find it? And what would it even look like? In 1999, a group in Vienna sent whole molecules through a double slit, and we should be clear about what that means. Not electrons this time. Carbon molecules made of 60 atoms each, roughly a nanometer across, objects with an inside and a shape, and a definite mass. Every one of those carbon molecules produced a clean interference pattern on the screen that was sitting behind the card. Molecules, not particles, objects with a real mass of their own. That should probably have been the end of it, and it was not. By 2019, we had pushed the record to molecules of 2,000 atoms apiece, and the pattern was still there. Then our experiments moved off molecules entirely and onto mechanical objects. Small vibrating drums, machined out of silicon, each of them containing something like 100 trillion atoms, were placed into a single shared quantum state. Those drums are large enough for you to see them under an ordinary laboratory microscope. Not particles, machined parts, and we have taken the mirrors of a gravitational wave detector weighing tens of kilograms. We cooled their collective motion until it sat near the lowest state quantum mechanics permits. Think about the record time for running a mile. Every generation treats that number as close to the limit of what a body can do, and every generation turns out to be wrong about it. We build better tracks, better shoes, better training methods, and the number falls again. None of us has ever found the wall itself. What we keep finding over and over is the current state of our own equipment. And that is exactly the shape of our boundary hunt, decade after decade. Every time we improve the isolation of the equipment, the size at which quantum behavior survives goes up again. We have not found a wall anywhere in nature. We have found out how good our shielding is. So, if there is no boundary at all, what happens to the things on your side of the line? What happens to you? There is a serious way out of all this, and I think it deserves a proper hearing rather than a dismissal. The argument runs like this: perhaps the quantum wave function is not a description of a particle at all. What if it never was? Perhaps it is a description of what we happen to know about the particle in front of us. On that reading, measurement creates nothing. It simply updates our records. Nothing more than that. No physical quantity is undecided anywhere, and the strangeness lives in our bookkeeping rather than out in the world. Serious physicists hold that position today, and they are not confused people. Would you dismiss them? It has the enormous advantage of removing every uncomfortable sentence about matter that we have just been through. But here is the assumption sitting underneath it, and it is worth pulling out into the light. The argument treats knowing about a thing and the state of that thing as two clean and separate categories. Think about asking somebody how tall they are. It is a fact about them. It sits there whether you ask or not, and it does not change according to what else you happen to ask alongside it. Ask about their height and their address in either order, and you get the same two answers back. That is what having a property means to all of us. Now, look at what our particles actually do. I want to be careful here, because this part is a theorem and not an opinion. We have a result called the Cochin-Specker theorem, proved in 1967. It shows us something very specific about any quantum system. The value we get for one property of a particle depends on which other properties we choose to measure alongside it. Change the pairing of the measurement and the answer changes. Not because our detector jostles the particle in passing. Not because the measurement is clumsy. Not because we lack precision. Because no consistent set of particle values exists at all. No assignment of quantum values that lets every answer sit there in advance, waiting for us. So even the modest reading has to swallow it. Our ignorance changes shape according to the question we ask. An ordinary ignorance does not behave that way. Yours does not behave that way. Neither does mine. So we have now run out of comfortable readings entirely. What is left for any of us to open? Let us put all of this in one place before we move on, because I think the sequence matters more than any single step in it. We asked whether a particle carries its properties in advance, the way your coin under a palm does. Bell turned that question into a number we could count. Just a correlation between two particle detectors, standing far apart. How often do the answers agree? Aspect measured the number, and it came out on the wrong side of the ceiling. Not close to the line, not arguable, wrong side. Our choice of measurement can be made after the particle has already gone through, and the result still follows that choice. We have found no boundary between the small and the large, only better shielding on the equipment. Molecules of carbon first, then silicon drums, then mirrors of real mass, weighing tens of kilograms. And reading all of it as simple ignorance about the particle fails too, because that ignorance changes its shape according to what we ask. So is the hidden part of reality only what we cannot reach? Some of that mass and energy appears to be what has not been fixed yet. For most of a century, this stayed an argument among physicists, and nobody else cared. Now, look at what we are doing with it. Think about a machine in a workshop that has always made a strange noise. You know the kind of noise I mean. Everybody has heard one. Everybody works around that noise. You write it off as a quirk, and the sensible people around you stop asking about it. Then somebody works out that the noise is not a fault at all. The whole machine could be rebuilt around it. Suddenly there is a product, a market, and a queue of buyers at the door. Nothing about the noise changed. What changed is that we stopped avoiding the noise and started building the business on top of it. That is where quantum computing comes from. The entire industry exists to hold matter in that undecided quantum state, at larger scales, for longer, deliberately, and at commercial volume. On purpose, at scale, for money. Do you see what any of us is actually selling here? We are not studying this anymore. We are engineering with it, and you are going to be sold the results. We are about to open the only door in the house that has never been opened. Nobody ever told us why it was closed. Go back to Herschel for a moment, and to the thermometer he slid past the red end of the spectrum and into the dark. I think that single move is the whole of what our species has done ever since, over and over. Every time we could not detect something with the senses we had, we built ourselves a new one. And every time the new sense worked, the room got bigger and stranger. In the last 100 years, we have done it more often than in all the centuries before us, and we are still doing it right now. We grew ourselves an ear for gravity, and I still do not think we have absorbed what that means. In 2015, a pair of detectors registered a distortion of space itself. It was a ripple thrown out by two collapsed stars spiraling together over 1 billion light years from your chair. That is not light. Not radiation of any wavelength. It is the geometry of space itself moving, and until that morning in September, no human being had ever sensed such a thing. Not once, not ever, not with any instrument. Next came an eye for the particles that ignore matter entirely. Do you remember Pauli apologizing for inventing something nobody could ever detect? We went ahead and built the detector anyway. A full cubic kilometer of ice at the South Pole now sits watching for the faint flashes that neutrinos leave behind them. Some of them arrive from outside our own galaxy. They carry energy out of places nobody can see and nobody has ever mapped. And we grew a wider eye for the sky itself. Our newest observatories now survey the whole visible sky repeatedly, night after night, comparing what moved and what changed since yesterday. Think about a house you have lived inside for years with a single window in it. You know that one view completely. Every roof on it. Every tree standing in it. Then somebody cuts a second window into the opposite wall. Everything you believed about your own position was a guess made from one direction. The house itself did not change at all. Only your account of it changed. 4 or 5 entirely new windows have been cut into that house in the last century alone. And how much should any of that comfort us? So here's the question that finishes all of this. Each new sense was supposed to bring the world closer to us. Did a single one of them actually do it? The morning of the 14th of September 2015 is worth sitting with because of what physically moved that day. We had 2 detectors running, one in Louisiana and one in Washington state. Each one is built as a pair of tunnels 4 kilometers long, meeting at a right angle. A laser runs down both arms, bounces off mirrors at the far end, and comes back to us again. Do you know what we were listening for? If our 2 arms stay exactly equal in length, the returning radiation cancels itself out and our instrument reports nothing at all. That is the whole design of it. We built a machine whose only job in the world is to notice a difference in length between 2 tunnels. That morning, we watched our arms stop being equal for a fraction of a second. One arm stretched out, the other one shortened. Then we watched them swap, back and forth, in a rising pattern that lasted about 1/5 of a second before it stopped. Then silence again, and the arms were equal. The arms were... The size of that change is the part I cannot get past. Our arms moved by a distance thousands of times smaller than a single proton. Smaller than an atom, smaller than a nucleus. Small enough that we should never have been able to see it at all. For us to notice that across 4 kilometers of tunnel is roughly like measuring the distance to a nearby star, and then spotting a change the width of a hair. Now, think about standing in a doorway while the whole house briefly gets taller and narrower, and then returns. Your body would register nothing at all. No sound at all, no shudder, nothing on your skin. Nothing in the mass of that building would ever have told you. And yet, it happened. To the doorframe, and to your bones, and to the ground underneath, all at once. That is what a gravitational wave does to us. It does not push through space. It changes the size of that space, and of every atom sitting inside it. Our source was 2 collapsed stars of enormous mass, spiraling and merging 1 billion light-years away. I want you to hold what happened next. For a fraction of a second, the energy they released was probably greater than all the light from every star in the observable universe. Every star, every galaxy, combined. So how much of that energy did we actually see? Nothing at all. And why would that be? Because we had nothing there to see with. That is the whole of the answer, and I think it is the most important line in this act. The most energetic event we have ever recorded released almost none of that energy as light. None of it as radiation, at any wavelength, in any part of the spectrum. All of that energy came out as the shape of space itself. And the shape of space is not something any eye evolved on this planet was ever built to register. And had we not spent 40 years building that machine, the loudest event in the observable universe would have passed straight through every one of us. No trace at all. No record. Nothing anybody could ever find. And was it a one-off event? Not remotely. Since 2015, we have logged well over 100 more of them, and the rate keeps climbing as our detectors improve. Every month now brings us another one, then another. Every one of those events is a collision between masses that we cannot detect by any other means we possess. Not one telescope, not one wavelength of light. Collapsed stars and the remains of stars, merging out in the dark where nothing shines and no telescope has ever usefully pointed. Some of those masses turned out to be larger than our own models comfortably allow. Others sit inside a mass range that we had confidently ruled out beforehand. Now, think about opening a drawer in a house you have owned for 20 years and finding the thing full to the top. Your first feeling is relief. You have found whatever was missing from the house, and the account finally balances again. The second feeling arrives about a minute later, and it is much worse. You never knew that drawer existed at all. So is your question still what is inside that drawer? It cannot be, and it never could have been. Not once you know the drawer is there. The only question left is how many drawers this house of yours actually has. Nothing inside the house will ever tell you. So that is what our new sense of gravity actually delivered, and I do not think it is what anybody expected. Not a shorter list of unknowns for us, a longer one, and for the first time in history, a properly measured one. So it has happened to us all over again. Every time we open a new channel, the same thing occurs. And why would that keep happening to us? The second sense we grew is stranger still, and I think it is because of what we had to use as the instrument. Remember our problem with neutrinos. They almost never interact with matter, so a small, precise device is useless to us. You cannot focus a neutrino and you cannot reflect one, so there is nothing there for us to make more sensitive. No lens helps, no mirror, nothing. What we need instead is an enormous quantity of matter sitting in the path. Then, enough patience to wait for one particle to strike a nucleus by accident. So we went to the South Pole and started drilling into the ice sheet. How large would you have to make a thing like that? The detector we ended up with is called IceCube. It is a cubic kilometer of Antarctic ice, and threaded through that ice are more than 5,000 separate light sensors hanging on long cables. We lowered every one of those sensors 2.5 kilometers down through the drilled ice, into the dark, under the pole, where nothing else goes. We built nothing at all. The ice was already sitting there, and it had been sitting there for 100,000 years. All we added was the ability to notice. I find that the strangest instrument on the planet, when a neutrino does strike, it produces a charged particle moving faster than light, travels through ice. That leaves a faint blue cone of radiation behind it in the dark. Our sensors catch that cone of light, and the geometry of it tells us roughly which direction the neutrino came from, which star it came from, which galaxy. Think about measuring how often a rare kind of rain falls on you. You cannot build a cleverer raindrop catcher, because the drops were never the problem. So you put out a bigger tray, and then a bigger one, until that tray is the size of a whole field. At that point, your instrument has stopped being a device. It has become a sheer quantity of matter. And what you learn is no longer about your equipment. It is about the sky. In 2023, we produced the first picture of our own galaxy taken in neutrinos rather than in light of any wavelength. It probably does not look like the galaxy any of us knows. That familiar band of stars is not the bright part of the neutrino picture at all. So which version of our galaxy is the real one? And how would any of us tell? The third sense is the one we already had, pushed so far that it changed character on us. On a mountain in Chile, we now have an observatory named after Vera Rubin, the woman who found those flat orbital curves in the galaxies. Her name now sits on a telescope, built partly to map the dark matter she first measured. Its telescope carries a mirror over 8 meters across and a camera holding 3,200 million pixels. That is not a small increment on the telescopes we had. It is a different category of instrument entirely. It photographs the entire southern sky every few nights, and I still cannot quite absorb that we intend to keep doing it for 10 straight years. The output is roughly 20 terabytes of raw data every single night of operation. Do you know what that produces? It produces something nobody in the history of astronomy has ever had to deal with before. Because we image the whole sky again and again, we can compare tonight against last week directly. Every star, every galaxy, every moving mass in the sky that brightened or vanished gets flagged for us automatically. The expected rate is around 10 million alerts every night, and I want you to hold that number for a second. 10 million objects in the sky that changed, every night, for a decade. Now think about the post arriving at your own house every morning. At first you read every letter that comes through the door. Then there is more of it, so we skim. Then more again, so we hire somebody else to sort it. Then the volume passes what any staff could possibly read, and something quiet happens that nobody ever announces. We are no longer informed by that post. We are merely in possession of the paper. The letters keep arriving, and the information inside them stops reaching anybody at all. That is where our observation now sits. No human being will ever look at most of the radiation these instruments collect. The sorting is done by software, and our software can only flag the kind of galaxy or star that somebody thought to describe in advance. So we have solved the old problem of not seeing enough of the sky. What we have instead is a different problem, and it is worse. So what happens to the things nobody wrote a filter for? Where does that mass go? And who ever goes looking? Now, let us do the one piece of arithmetic that all of this has been building toward. I think it is the number that matters most, and probably the only one worth remembering. Not what we know. What fraction of the mass and energy of this universe we can actually account for, and how that fraction has moved over time. In 1900, we would have said all of it. The universe was stars and gas made of atoms. Our physics described how those atoms moved. Our chemistry described how they combined, and the whole accounting balanced. Call that 100%. Then Zwicky counted the mass of the Coma cluster, and our two numbers did not match. Do you remember that cardboard box in the hallway? I keep coming back to it. Then Rubin found the same gap in every galaxy she measured, one after another after another. Then our supernovae came back too faint, and something we cannot name was pushing space itself apart. Every one of those was a better measurement, taken with better equipment by people who were not making any errors. Nobody was careless. Nobody was fooled by anything. Nobody was guessing. And after every single one of them, the fraction we could account for went down. Today, our honest figure is around 5% of the mass and energy in existence. 5 out of 100. Again, and worse. Not 5% of what we have looked at. 5% of every particle and every field that exists anywhere. Think about measuring a coastline. You walk it with a long chain and you get a number. Then you use a shorter chain. It fits into the inlets the long one skipped over, so your coastline comes out longer. Use a shorter chain again, and your coastline grows longer still. Most measurements settle down as we improve them. This one runs away from us, and the running is not a fault in the chains. It is a property of coastlines themselves, and no amount of care on our part will ever make it stop. That is what our accounting of the mass of this universe has been doing for a century. Every improvement to our instruments has increased the measured size of what we cannot explain. And it has increased that number faster than it ever added to what we can. So has anything ever gone the other way for us? Has any new sense in history ever closed a gap instead of opening one? It has never once gone the other way. And I want us to walk the history, because the shape of it is the same every time. In 1610, Galileo turned a new instrument on Jupiter and found 4 small points of light going round that planet. It was the first time any of us had watched something orbiting a mass other than the Earth. Do you see what that one observation did? Did that settle our picture of the sky? It ended our idea that the sky above us was a finished thing. In 1835, a philosopher argued that there was one thing we could never know, and that was what the stars are made of. He seemed obviously right at the time. You cannot carry a star into a laboratory. Within 30 years, we were reading the chemical composition of starlight straight off the spectrum, and the method worked perfectly. It also turned up a line in that spectrum matching no element on this planet, and we had to invent a new one to hold it. In the 1920s, the faint smudges in our telescopes turned out to be entire other galaxies, each one full of stars, each one carrying its own mass. In a single decade, our universe went from one system of stars to billions of them, billions of galaxies, where we had carefully counted one. In 1964, 2 engineers cleaning a horn antenna could not get rid of a faint hiss in the signal. They checked the wiring, then the birds nesting inside the horn. They went in and cleaned out every last trace of the droppings from inside the metal antenna horn itself. The hiss stayed. It did not move. It did not fade. That hiss was the background radiation left over from the early universe. Nobody was looking for that radiation. Nobody had asked. It was simply there, and it had always been there. Think about walking up a long hill. Near the top you can see the ridgeline, and you tell yourself, that is the last of the climb. Then you crest it and there is another ridge sitting behind. Then another one behind that. The land was always shaped like that. The climbing is what keeps producing our view of it, and I do not think we ever notice that. 400 years of this, and every single time it takes the same shape. So we come to the last question of all, and it is about you rather than about the sky. So what is all of this actually telling us about ourselves? The obvious objection to all of this is that it sounds defeatist. I want to answer that properly rather than brush past it, because the objection is a good one, and it deserves the time. Does science work? It works spectacularly well, and it works on real matter. We predict eclipses to the second. We fold proteins and design molecules atom by atom. We put a machine on another planet and drive it around for years. The device you are hearing this on is built out of quantum mechanics and semiconductor physics, and it does not fail you. Nobody sensible argues with a single word of that. So is that progress real? Of course it is. But we should ask what all that progress has been converging on, because I do not think it is what we assume. Think about somebody 30 years into a trade, and about what you would hear if you asked them. Ask an apprentice how much of the work they understand, and they will say most of it, and they will mean it honestly. Ask the person who has done it for 3 decades, and they will tell you they are still learning it. We usually read that as modesty. It is probably not modesty at all, and I think we get this wrong constantly. Your apprentice cannot see the parts they are missing, while the older one has spent 30 years learning where those parts sit. One is guessing. One is counting. Both sound honest. And the difference between those 2 answers is not humility. It is accuracy. That is probably what has happened to all of us as a species over the last 100 years of physics. Our command of the accessible 5% of the matter in this universe has grown enormously in a century. Our estimate of how much of the mass and energy out there is accessible at all has fallen just as hard. Both statements about our physics are true at once. There is no contradiction anywhere between them. And that is the uncomfortable part for all of us. Getting better at measuring particles and radiation is exactly what revealed the size of our gap. A worse century of measurement would have felt far more complete than this one. So our growing ignorance is not a failure at all. It is a measurement of the mass and energy we cannot reach, and we produce that number ourselves. So that leaves one last thing for us to settle. What is left of the word that all of us started with, right at the beginning of this? 6 separate times now we have taken something away from you, and I want to name each one of them before we finish. Your eyes report a sliver of the electromagnetic spectrum, and they were built for speed rather than for truth. 99% of the signal never even leaves them. The matter that holds together every structure you belong to has never once been caught in any detector we have built. The distance between all things is growing. Most of the galaxies we can see have already crossed beyond our reach forever. Empty space turned out not to be empty, and our best theory misses its energy density by 120 digits. Properties of a particle do not appear to exist at all until something interacts with it. And every new sense we grow reports a larger unknown back to us than the one before it. 6 separate removals, no returns anywhere in it, nothing given back to us. So look at what has quietly happened to a single word through all of that. Do you still trust that word? Should any of us? In ordinary use, the word reality means whatever matter and energy is actually there. That is how you use it, and how I use it. And neither of us has ever once had a reason to check. Now, think about a passport photograph of yourself. It is a true image. Nothing was faked. The light was real, and the face in it is yours. And yet nobody on this planet would ever call that photograph a description of a person. Every one of us knows instinctively that the thing captures one angle in one moment under one kind of light. Now, notice what we have probably been doing with the whole universe for 400 years. We took the report of one narrow band of the radiation reaching us, gathered by equipment tuned to the output of a single star, filtered through one atmosphere, assembled out of seawater. And we have been calling that report reality. It is not a false report of anything. It is a passport photograph of the universe, filed away under the name of the thing itself. So the answer to the question all of us start with may not be that most of reality is hidden from view. It is that the word itself has been doing a job that it was never able to do for us. And that changes what the last 100 years actually were. So what exactly were we doing all that time? Go back to the room where all of this started. The one you are sitting in right now. Nothing about that room has changed in the 2 hours we have been talking. Has anything moved at all? The walls are exactly where they were. The light coming through the window is the same light, at the same wavelengths, doing the same work it did before we started. Nothing moved in there. Nothing broke. Nothing arrived. And every single thing we have talked about is happening inside it right now, while you sit perfectly still. 100 trillion neutrinos are crossing your chest every second. Not one of those particles will ever touch a single atom of you. The dark matter holding this whole galaxy together is passing through the floor beneath your feet and out the far side of the planet. The space between you and the far wall is growing as we speak, slightly, permanently, irreversibly. The vacuum between your hands is not empty. Its energy is pressing on every surface and every atom in that room. And every particle of matter you are assembled from carries properties that may not be settled until something interacts with them. None of that is far away. Is any of it waiting to happen? None of it is waiting for anything or anybody. All of it is simply the ordinary condition of an ordinary afternoon. So we come back to the question we opened with, and I have carried that one the whole way here with you. Are we looking at the world, or only at the small part of it that agreed to talk to us? I think we probably have our answer, and I think it is worse than the question implied. Because that question still quietly assumes there is a conversation happening between two parties. Look hard at the word we have all been using this whole time. Hidden. that word needs somebody to do the hiding. It needs an intention behind it, a decision, something that chose not to be seen. And in everything we have looked at tonight, we have not found a single one anywhere. There is no adversary anywhere in any of this. Nothing anywhere is withholding anything from us. The asymmetry is entirely on our side, and I think it always was. The invisible was never hiding from us. It was never the thing that needed to be found. We are the ones standing in a dark room, holding one match, calling it daylight.